Greetings, this is Phi with another log entry on our polynumbers project. So what you're looking at on the screen right now is a plot of 32 polynomial curves from the spread polynomials, and they are plotted in two colors. But you'll also notice that there are some white dots on the screen. So these dots represent points that, up to this point, I've been able to determine as algebraic points of this system. And I just want to make a comment here. As I've been working on the Geometry Explorer modules and libraries, I've come to think of points as really the core of the information of a system that we're examining. It's really the only information we have. Everything else is the rule by which we can generate information. So in order to know where a point is, we need to find where it crosses, where one curve crosses another, or one line crosses another line, or where one circle crosses another line or circle. We can't tell anything else about any of these functions until we can identify some kind of a crossing. And so here, these points, as we see, are truly either rational. I'm surprised at how many are rational within this field, or they are algebraic. So here in this case, you can see this one has elements of the square root of 5 in it, the proportions of the square root of 5, I should say. This one is rational. This one has the square root of 2 involved in it. This one has, again, the square root of 5. This one has the square root of 3 involved. And the same on the, you can see on the heights as well. Sometimes the height is a rational number, or sometimes it is not. And it's really quite interesting to look at this. I think one thing that's been obvious all along is that there are these axes that are running through this figure that are really quite dominant. So we have a dominant one in the center. We have another dominant one here at this 1/4 location. We have, this one is not a rational point. I was going to say sometimes they're rational points. Maybe this one is. No. Anyway, I'm still learning what all of these are. But we have 32 curves that are generating right now 54 algebraic points, right? And you may say, wait a minute, they're not all intersections. I'm also, in addition to the meets for two polynomials, I'm also looking at the roots of the polynomial and the vertices of the polynomial. So in those cases where we can find an algebraic value, I am gathering those and then plotting them on the screen. Now, with SymPy, this is about as far as we can get with an actual algebraic solution. I'll show you what SymPy does when it can't figure things out. We can generate a numerical intersection for every single intersection that you see here on the screen. It's an enormous number. I haven't collected them yet to see, but you'll see as the code is running, there's going to be an enormous number of them that are generated. And it will be interesting to look at them too. I don't know what else we can tell about them, but I suspect that some of these points, we may be able to predict what their values are, and particularly if we can look at what the numerical equivalent is, that we may be able to figure out what the algebraic value is that satisfies the intersection, and so that could be pretty interesting. I know this is the solving of polynomials has been a big a big project for Dr. Weilberger, and I'm trying to think through now. So if we have a collection of things and we want to see how they interrelate with one another, we should have good tools that can help us to do that. And so I think this is the first step. As I mentioned in a previous video, we're looking to model, analyze, and render, and we're doing pretty well on the ends, and now in the middle, now we've got to start taking a look at things. So all of these points, we can start to find commonality across them. You'll see that there's definitely vertical lines that are being established by the points. There's also horizontal lines that you can see here, and I think once we can get those into collections, we can start to analyze those sets of points. I am sure that we have cross ratios, that are happening within, various aspects of this. And maybe there are other lines that we don't see readily. We can ask all the points in relation to one another, whether they form a line or not, or of more than 3 points maybe. And so there's a lot to consider here. And it's pretty exciting to get to this point. So 54 known points within 32 curves. So that's a benchmark for us, and see if we can actually do more. So let's take a look at some code now, and we're going to run this in real time, and I'll show you what SymPy is doing. It's really kind of a miracle. So I'm going to quit out of this, and we'll jump into our code. Let me make this a little bit bigger, I think. So, get my focus right. Okay, so we were running our 32 curves here, but I'm going to make this down to 8 as we go through, and I'll keep the number of divisions the same. That is fine. So we're generating our set of polynomials. We're creating each one for the indexes from our count here, and in the for loop. You'll see that I've got queued up some other polynomial curves to study too, and we'll get to that in another video. It's really very interesting. So here we get the expression out of the polynomial, and we append the polynomial to a list. If it has coefficients, then we are adding those to a list, which we're eventually going to build a matrix out of. I probably will be doing that right here. So again, this is still all kind of being done on the fly. We're figuring things out, but the next thing is to take a look at our try to find the root points for the curve, then the vertex points, and then the meet points. So let's go and look at that code. Should be able to just jump right there. Nope, I'm not going to jump right there. Oh, yes, let me save that and jump over to that. Okay, so we have 3 functions here. Our first one for meet points takes 2 polynomials, subtracts them from one another, creates a function, and then asks that subtracted polynomial for its roots. We take a look at each one, try to simplify it first, just in case it's got some weird stuff in it. Then we ask if it's algebraic, and if it is, then we generate a point out of that. And if it's not right now, I'm just printing the floating point values to the screen. And again, we may want to collect those into a list and do some further analysis on that later. For the roots, just basically doing all of that for each individual curve, pretty much the same process. So I think that we can do some refactoring here and tighten up these functions for sure. Right? There's a lot of redundant code, and then we are finding the vertexes, which we take our polynomial is passed in, form a differential, and then create a function out of that, and then we find the roots for that. Okay, and then we also later we're going to look at our conic formula, but that's it for basically finding these points that we are working with. If they're algebraic, they're getting added to the list. My Geometor point manager, when it's adding to the global points list, will do deduplication, right? So if it's going to check to make sure that there isn't another point in there, and if there is, it's going to add that point's parents to the original point's parents, and will give us an ancestral accountability across all of our objects, right? So let's see. All right, and then we plot the whole thing, and not doing much else here, and then print our stats here at the bottom. So we're set to run 8 curves. Let's just go ahead and do that. Hit F5. It's just asking me where do I want to put this, and then it's just going to start generating stuff. But let's stop here. I'm going to scroll back. Let's go right back up to the beginning. Okay, so our first polynomial is just the value of x, and it has the roots 0, 0 here. And our second one is 4 times x squared plus 4x, and has the 2 roots that you see. It's vertices are being identified. Most of these lower degree polynomials are working really well and are doing everything very accurately, across here. Third degree, as you can see. So for the meets, what I'm doing is for every new polynomial, I'm testing it against the ones that came before. So we're going to now subtract this one from the first polynomial, or this polynomial here, from the first polynomial. That gives us this equation, and we get these roots out of it. And then we test that against the second polynomial, and we get these roots out of it. So it's really pretty simple, pretty straightforward. And looking forward to really diving more deeply into this and understanding what's going on. So now let's see, our original curve here is of a fourth degree, right? And we've got a meet now. When we subtract this third degree polynomial from the fourth degree polynomial, we get this one. And this one is only able to come up with one algebraic root. The rest of them are being expressed in this complex root of equation. And I don't quite understand all of this and what SymPy is doing here. I've noticed in some cases where I see this that the result is clearly an algebraic value, but why SymPy can't figure that out, while sometimes it can, is going to be something interesting. And I'm maybe hoping to share this with the SymPy forum. I think they'd be quite interested, actually, in what we're doing with their platform. It's pretty fun. So anyway, this is what it does, just going through one polynomial at a time and testing it against all of the others. And I think all of these equations would be quite interesting to examine further, see what we can do there, and find the patterns. We're looking for patterns, right? So coming all the way down to the end, we see it's still running here. And it takes quite a while. If you think about, we're doing a factorial process here, right? And it's going to take a while to generate all of this information. And it seems to be a little slower too, probably because I'm recording. But one of the things that I will be looking at shortly, and I've done this on the Explorer modules already, is to parallelize some of this work. Right? So these functions are highly independent, and we can, if you have eight processors or virtual processors on your machine or whatever you've got, we can split this work up and get them all working on this, and it will speed things up considerably. I've done that for the Euclidean geometry libraries that I've been working on, and it's been working very well. Python is, people complain that Python is slow, but I don't know how to do some of this stuff otherwise. I mean, maybe there's stuff out there, but it's pretty amazing at what we're able to do. And this mathematical work is very functional, so it's very parallelizable, and we can drive this hard. We can create large compute clusters to explore this further. Once we figure out what the logic is for that. I'd had a bit of experience in doing that kind of work at one point in my career. It'd be really interesting to turn that to this problem. So I hope that I did this right. I wonder if I forgot to. Oh, I see. I think we're still running 32 here. Anyway, I think it's going to keep going. I thought I changed it to 8. Maybe I didn't. We're running way more than 8 curves right now. So anyway, maybe we'll just end it here. This is Phi with another episode, and I think the next time either going to dive into this and clean this up a little bit more. Very interested also in plotting the corresponding ghost curves from the work that Federico did. And yeah, I think that's what we've got for today. So until the next video, Let me know what you think about all of this. Thanks a lot. This is Phi. Out.